Hello there, and welcome to the Whispering Science. Tonight, we're going to sink slowly and serenely into the mysterious world of entropy, that subtle, invisible force that pulls at the fabric of all things, organizing, unraveling, and guiding the grand dance of the universe. From the swirl of our own breath to the silent drift of distant galaxies. Now, I do hope this isn't too interesting that it keeps you awake. But if it does, well, at least you'll have learned something fascinating about the secret currents shaping your world and everything you'll ever touch. Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. Your small gestures help keep these quiet explorations alive for wanderers like you. So settle in, get comfortable, and let's begin our quiet voyage into today's topic, entropy, while the world hushes and you drift into restful awareness. What exactly is entropy? You might have heard this word whispered in hazy science classes, or perhaps it pops up in curious places, like a novel referencing the entropy of a relationship, or a news article about the heat death of the universe. But in the clear, cool light of science, entropy has a simple, profound meaning. One that's woven into the very laws that govern everything from the simplest grain of sand to the boundaries of cosmic order. At its root, entropy is a quantitative measure of disorder, or, more precisely, the number of specific ways a system can be arranged, often while still appearing the same overall. Imagine you have a deck of playing cards, neatly stacked in order from ace to king. That's a low entropy state. There's only one way to achieve this perfect sequence. Now, you shuffle the deck thoroughly. Suddenly, there are more ways, almost unimaginably many, to arrange those cards while still just calling it a shuffled deck. That's high entropy. In the physical sciences, entropy often gets associated with disorder, but it's richer than that. It counts the probability or the possibilities, the hidden microarrangements beneath the tidy surface. Think of entropy as the universe's preference for possibilities. Given a choice, nature always seems to favor the side with more options. Water explores every twist and turn down a stream, heat leaks away from your bath, and perfume spreads out to fill every corner of a room. These things happen not out of malice or magic, but because there are simply more ways for molecules to be widely spread. And that means higher entropy. In formal terms, entropy is represented by the symbol S, and was first introduced as a scientific quantity in the 19th century. Think of it as a kind of invisible bookkeeper, quietly keeping track of how energy spreads out and how arrangements multiply, without changing the total amount of energy itself. It doesn't measure energy, but rather how that energy is dispersed. Not just how much there is, but how many different ways it could be scattered. For instance, a hot cup of tea loses its heat to the air, not because the universe wants cold tea, but because there are simply more ways for the heat energy to spread out into the tens of billions of air molecules than to remain locked up in your cup. Entropy isn't a villain. It's not out to undo your plans or foil the tidy organization of your closet or your calendar. Instead, it's a silent rule, an impartial force equalizing energy and maximizing randomness wherever it can. And it's relentless, not because it chooses to be, but because it's built into the basic statistics that guide how atoms, heat, light, and information shift and shuffle around. To make it even more personal, every time you breathe out, or stir a spoonful of sugar into your tea, or simply lie quietly in the dark while your body radiates the gentlest whisper of heat into the sheets and the air, entropy's rising, bit by bit. In fact, even the very act of life itself, of every cell organizing, dividing, metabolizing, is just a temporary defense against entropy's wider, patient march. Life creates temporary islands of order, but the universe as a whole always trends toward more dispersal, more mixing, more possibility. So next time you hear the word entropy, you'll know it isn't some shadowy doom or abstract menace. It's the great leveler, the deep mathematical principle guiding every process of change, every spread of energy or mixing of molecules. Invisible, constant, and absolutely fundamental, it's the quiet pulse behind the music of reality. Why does entropy matter? In the gentle tapestry of the world around you, from the most mundane household acts to the most sublime cosmic events, entropy quietly shapes every process without exception. It matters not because it bellows its name or makes itself overtly known, but because it weaves its influence through each transformation you witness, every cooling cup, every burning star, and the very directionality of time itself. Begin, if you like, close to home. Picture yourself making breakfast on a chilly morning, your hands wrapped around a steaming mug. The heat that seeps from the mug doesn't fade away by chance. It's entropy at work, guiding energy from a place of concentration and structure into diffused, imperceptible warmth throughout the kitchen. It's why your ice melts in water instead of spontaneously reassembling into a cube, why your bread stales, why your cozy room grows cold if the windows are left open. Entropy is at the root of every energy transfer. It determines why processes run the way they do, always flowing from more concentrated, useful forms of energy to more scattered, less harnessable ones. But the reach of entropy doesn't stop at the breakfast table, or even at the edge of your neighborhood. Entropy's influence stretches from the orbits of electrons in atoms to the vast, spiraling arms of galaxies. Take the stars you see when you glance out at the night sky. Each one is a titanic engine, burning through fuel at unimaginable rates, shining because of the relentless drive to transform concentrated nuclear energy into diffuse light and heat. As stars burn, entropy inexorably increases. The concentrated hydrogen is transformed into helium, and the released energy floods the surrounding cosmos, making the night eternally, minutely warmer. If you travel even farther out, entropy is there at the birth and death of worlds. Planets come together from clouds of dust and rock, not in spite of entropy, but because of it, as gravity and energy exchanges drive the formation of more stable, albeit more randomized configurations. Supernovas, those brilliant deaths of stars, represent entropy on a phenomenally spectacular scale. In their last moments, a star's matter and energy are flung outward to fuel the formation of new stars, planets, and perhaps even the building blocks of life. Each of these transitions increases the total entropy, spreading energy and matter more widely and more randomly than before. Let's gently fold in a surprising fact. The second law of thermodynamics, rooted in entropy, means that once energy spreads out, it cannot all be corralled again. No matter how elaborate our machines or how clever our designs, there's always a portion of energy we can never fully reclaim. Every car ride, every glowing lamp, every breath you take represents some energy transformed in a way that can't be perfectly reversed. Carefully generated order slipping, grain by grain, into dispersal. Even in the smallest places, inside your own body, entropy governs your deepest processes. Every heartbeat, every blink, every neuron that fires is a tiny, temporary ordering of energy, soon paid back by the shifting of atoms and release of heat, so that overall across your life, entropy in the wider world still increases. And yet this isn't something to fear or resent. Entropy isn't the enemy of life, but its context, a stage on which every living system, each cell, each creature must find ingenious, sometimes beautiful ways to sustain their own patterns, if only for a while. But why should you, in the quiet hush of this evening, or the stillness of your room, truly care about entropy? Because by understanding it, you gain a sharper lens for seeing the secret threads that shape your world. It explains why perpetual motion machines can never work, why batteries lose charge, why cakes bake and never unbake. It reveals the hidden logic behind the direction of time, the end of stars, and even the subtle unfolding of memory and information. Most profoundly, entropy teaches us humility and wonder. It connects your daily experiences with the deep cosmic currents of change. It grants context to every moment of order, to every carefully cleaned room or freshly set table, by reminding us that such moments are brief, crafted pockets of low entropy amid a world destined for deeper randomization. Entropy tells you not just how things change, but why change itself is woven into the universe. All things move toward greater possibility, wider dispersal, and deeper mixing, not because of accident, but because entropy matters everywhere, always. So as you drift now into a gentler state of mind, Know that entropy's influence wraps around you, subtle, mathematical and beautiful, linking your warm breath, your cooling tea, and the shining of the farthest stars in a single, unbroken story. Tracing the word entropy opens a gentle window onto not just how science works, but how the very language of discovery evolves alongside our understanding of the universe's secrets. The word itself, entropy, sounds both grave and mysterious, yet its roots are remarkably straightforward, tethered to humankind's need to find order, pattern and meaning as we grapple with the unseen rules that govern reality. The journey begins in the 19th century, a time when steam engines powered factories and trains, and the world was busy measuring, weighing, coaxing more work from coal, and wondering why engines could never run with perfect efficiency. Physicists and engineers alike were perplexed. Where was the lost energy going? And how could there be such an inexorable slide from useful, concentrated energy to diffuse, unusable heat? It was a German physicist named Rudolf Clausius in 1865 who first coined the term entropy. Clausius had already been working with the concept for years, intent on quantifying the energy loss that seemed to hound every real, practical system, no matter how carefully constructed. He borrowed the Greek word trope, meaning transformation, and paired it with en, for in or within, creating entropy, the content of transformation. In Clausius's hands, entropy became a mathematical marker of irreversibility, a kind of scorecard for how much energy in a system could no longer do useful work. For the first time, entropy gave scientists a way to count, to reckon with the subtle losses that seem to accompany every act of heating, mixing, or movement. Clausius's insight swiftly transformed the science of thermodynamics. By framing entropy as a precisely defined quantity with its own symbol, S, he gave engineers, chemists, and physicists the vocabulary and tools to predict how processes would unfold, not just whether energy was conserved, but how it would inevitably spread, thin out, and tumble toward greater randomness. When he famously declared, "The energy of the universe is constant, the entropy of the universe always increases," Clausius gave voice to one of the most foundational insights in all of science. That declaration, brief, stoic, and quietly profound, has echoed through every subsequent exploration of heat, work, and change. But entropy wasn't merely a technical term, bound for engineering tomes and classroom chalkboards. As years passed, its meaning blossomed and branched out beyond physics. The early 20th century saw Ludwig Boltzmann, another brilliant mind, delve even deeper. Boltzmann gave entropy a stunning new interpretation, rooted in statistics and the behavior of molecules in vast numbers. His famous formula, S equals sign K log W, is chiseled on his tombstone in Vienna, a quiet reflection of how significant this leap truly was. Here, W stands for the number of possible microscopic arrangements a system can take, while still appearing, macroscopically, the same. Boltzmann's work showed that entropy isn't just a feature of how heat moves, but is the measure of all possible arrangements, a profound link between invisible particles and the visible world. When you hear entropy used, even outside of science, when writers describe a story falling apart, or when someone remarks on a messy room as entropy in action, they're intuitively tapping into the core of what Clausius and Boltzmann work so hard to describe in symbols and numbers. It's a word that collects within itself whole centuries of questioning, calculating, and observing. It is a word that traces humanity's slow, patient realization that disorder is both inevitable and deeply meaningful, and that change can be predicted, quantified, understood, even if it can never be reversed. Interestingly, entropy's evolution as a concept didn't stop in the engine rooms and classrooms of the late 1800s. In the 20th century, it leapt into new disciplines entirely. In 1948, Claude Shannon, working far from steam and heat, repurposed the idea for his revolutionary work in information theory, using the word entropy to describe uncertainty and information content inside messages and data streams. Suddenly, entropy was not just about heat and molecules, but about bits, choices, and the mysterious richness of uncertainty, its roots deep in Greek, its meaning now as boundless as the cosmos and as intimate as a flicker of static on your radio. So when you rest tonight with the word entropy settling softly in your mind, let it remind you of the patient human journey toward understanding, of Clausius seeking the hidden cost of every transformation, of Boltzmann seeing order and disorder in every invisible dance of molecules, and of Shannon tracking possibility and surprise in every coded message. The word entropy is a bridge, linking ancient language to present-day science, crossing continents, centuries, and even the boundary between the physical and informational worlds. And tomorrow, when you hear someone mention entropy in passing, you'll know its origin and its journey. A word chosen carefully, forged in the heart of science, and still illuminating the gentle, persistent powers at work behind every change, every chance, and every gentle drift toward the future. Disorder and probability are two entwined threads that quietly underlie the true science of entropy. These are not just abstract words, but the very mechanisms that allow the universe to move and change in every moment, from the swing of a pendulum to the most distant flicker of starlight seen on a summer night. To begin gently, let's return to the simple example of a set of blocks, perhaps like those you played with as a child. If you set all the blocks on a table in a perfect single-file line, that's a very orderly arrangement. There are only a handful of ways to arrange them just so. Now, imagine you close your eyes, sweep your hand through the blocks, and scatter them across the table. Suddenly, there are countless ways the blocks can end up scattered, with almost no way to reconstruct your perfect line except by deliberately placing each block again. In scientific language, there are many more microstates, those tiny specific arrangements that make up the broader macroscopic condition of scattered blocks, than there are for the orderly line. Entropy, at its heart, is a way of counting those possibilities. This link between disorder and probability was sharpened beautifully by Ludwig Boltzmann, the scientist you've now met in name. Boltzmann realized that systems naturally evolve towards states that can be achieved in the largest number of ways. Order, like the neat row of blocks or a perfectly made bed, is special because it's statistically unlikely. Left to themselves, the building blocks of nature gravitate toward the most probable arrangements, those with the largest number of possible microstates. This is why your room, unless constantly maintained, tends to become messy over time. There are far more possible ways for it to be disordered, with toys here, socks there, and books askew, than there are precise pathways to tidy serenity. The universe offers no personal judgment about this increase in disorder. It simply follows the logic of probabilities, choosing, by default, the path with the most options. If you zoom in far enough to the level of atoms and molecules, the power of probability becomes even clearer. Take a box filled with just a handful of gas molecules. If, by sheer chance, all the molecules found themselves in one tiny corner of the box, we would call that a highly ordered low entropy state. But there are vastly more ways for those molecules to spread out and occupy the whole box, bouncing off the walls and each other in an endless, unpredictable ballet. So, overwhelmingly often, this spreading out is exactly what happens. The molecules mix and mingle, entropy rises, and the likelihood of returning, by chance, to that original corner huddle is so tiny as to be unthinkable in the time span of the universe. This is the reason for many familiar, seemingly irreversible processes in daily life. When salt dissolves in water, the salt ions disperse throughout, not because they prefer mixing in any conscious way, but because the mixed state corresponds to a fantastically greater number of microstates. Each arrangement of ions among water molecules being a new version of the same mixed reality. You could, theoretically, have all the salt randomly jump back into a corner of your glass, but that would require an astronomical coincidence, so improbable that it simply never happens on its own. This deep connection between disorder and the odds of various arrangements gives entropy its directionality and authority. It's fascinating and a little humbling to realize how deeply probability governs the world. right down to the heat seeping from your skin as you drift under your blanket. Heat, on the atomic scale, is simply the jostling, vibrating, and ever-shifting of countless molecules. As faster-moving particles bump into slower ones, their energies redistribute in random directions, averaging out over time. The possible ways these particles can share and distribute their energy are nearly limitless, and it is exactly this dizzying multitude of arrangements that gives rise to the arrow of time, the sense that things move forward toward greater entropy and never in reverse. Boltzmann's leap was to write this into the language of mathematics. His iconic formula, S equals sine K log W, says that entropy, S, is proportional to the logarithm of the number of possible microstates, W, the system can access, with K being Boltzmann's constant, a small number, but one that connects the individual quantum world to the macroscopic scale you feel and see. This relationship means that even staggeringly large increases in possible microstates show up as linear increases in entropy, making the concept practical, measurable, and applicable everywhere, from physics classrooms to chemistry labs and even into the tangled data of computer science. But let's bring this back to you, tonight, breathing softly in the quiet. Inside your own body, the molecules in your lungs, in your blood, and in each cell are constantly shifting and colliding, exploring trillions of different arrangements every second. The order that keeps you alive is precious and fleeting, always buffering itself against the vast probabilities that favor more randomness. When you eat, sleep, think, or dream, entropy is gently, unstoppably growing. Not in a destructive way, but as a matter of pure possibility. So the next time you marvel at a messy room reclaimed, or wonder why creased clothes so easily wrinkle again, remember that you live not in a world of fixed certainties, but in a tapestry woven from probability and potential. Entropy is the deep, statistical bellwether, showing which futures are most likely, and reminding you that the disorder you see around you isn't laziness or fate, but the ever-present, impartial verdict of numbers themselves. Energy dispersal is at the heart of entropy's quiet rules, a gentle but unwavering guide for how every spark, every warm touch, and every star's radiant shine must ultimately fade and spread. To understand why entropy is so inexorably linked to the flow and dispersal of energy, and why hot things cool down but never become hotter on their own, settle in and let's explore why nature always seems to prefer spreading over gathering, blending over concentrating, diffusion over segregation. Imagine for a moment a cup of cocoa resting on a table in your softly lit kitchen. The cocoa inside is steaming, sending gentle tendrils of warmth into the cool morning air. The heat in your cup doesn't vanish, but dissipates, atom by atom, molecule by molecule, into the room. Before long, your drink reaches the same temperature as everything around it. This is not just a common inconvenience, but an inevitable outcome of physical law. The second law of thermodynamics, rooted in entropy, guarantees that energy, left to itself, will always disperse as widely as possible. But why is this? To answer, let's peer into the microscopic world, into the busy shuffle of molecules that make up everything you see and feel. Thermal energy is simply the jostling, random motion of these countless minuscule particles. When a hot cup sits in a cooler room, its faster-moving molecules collide with the slower ones in the air, imparting energy, until on average, all particles, inside the cocoa and out, are moving at roughly the same speed. At that point, the system has reached equilibrium. There's no more net flow of energy between cup and air, and entropy has reached its maximum for this closed setting. This flow, the gentle, spontaneous spread of energy, is inevitable because there are vastly more ways for energy to be shared and randomized than for it to remain concentrated. In terms of entropy, the highly ordered state of a hot drink surrounded by cool air is far less probable than the disordered state of evenly shared warmth. So, heat always moves from hot to cold, from concentrated to dispersed, never the other way around, because it aligns with the arithmetic of probabilities and the rules of entropy. Let's look further, out across the woven threads of energy dispersal in other systems. When you turn on a light, electrical energy from the walls becomes light and heat, a little order, briefly visible, but mostly a diffuse, quiet warmth that seeps into the air. When wood burns in a fireplace, its chemical energy moves into the room as heat and light, but that energy also inexorably radiates away, making it impossible to collect and use it all over again in the reverse order. In the world of physics, we call this process irreversible, not because it's impossible by some mystical edict, but because the odds of all the gently dispersing, randomizing energy ever returning, unaided, to its original ultra-dense, concentrated form are beyond astronomical. Picture a droplet of ink falling into a glass of water and swirling in slow clouds. Nature allows endless ways for the ink molecules to mix with water, but there is only one way for all those inky molecules to jump at once back into a neat droplet, leaving clear water behind. It could, in theory, happen by chance, but the number of random rearrangements needed is so immense that the lifetime of the universe wouldn't be long enough to wait for it. This is reflected in nearly everything you touch or do. Car engines turn gasoline's organized chemical energy into the scattered energy of movement, noise, and exhaust heat, most of which is lost to the surroundings, irretrievable. Your own body works in exactly the same way. Cells transform the energy from food into chemical work that keeps you alive, but much of it radiates away as body heat, a consequence of entropy's firm, impartial accounting. Even the most advanced machines cannot fully escape the call of entropy. Engineers have spent centuries trying to invent perpetual motion machines, devices that run forever without needing more fuel, simply cycling energy endlessly. But every effort is thwarted by the gradual, relentless dispersal dictated by entropy. There's always friction, resistance, inefficiency, a little extra heat, a bit more randomness, a final step that can't be reversed. On the larger scales, energy dispersal is why stars shine only for a finite time. The hydrogen at their cores is steadily fused into helium, releasing energy, which radiates into space and gradually increases the entropy of the universe as a whole. When the fuel is gone, the star can never gather all its spilled energy and relight itself. In your everyday life, whether you're reheating a meal, running water in a bath, or feeling a breeze on your skin, energy is always on the move, slipping from concentrated hotspots to everywhere else, evening out, blending in, raising the chaos in a process that seems simple, but is ultimately guided by intricate cosmic arithmetic. So next time you watch cream swirl into your coffee, a whisper of fog lift off the bath, or dusk cool a sunny room, remember, entropy's touch is always there, directing the hidden flow of energy, orchestrating nature's preference for things to spread rather than cluster, and quietly shaping the fate of every flicker of heat, every spark of light, across all of space and time. How entropy emerged as a central concept in physics is a story woven from curiosity, careful observation, and a series of brilliant insights during the great age of industrial progress. In the early 1800s, as steam engines powered the arms of factories and trains raced across continents, scientists found themselves confronted with new and sometimes bewildering questions about the nature of heat, work, and irreversibility. Let's linger first with the name Sadi Carnot, a French engineer whose quiet focus in the early decades of the 19th century gave birth to the modern science of thermodynamics. Carnot sought to understand how engines could convert heat into useful work, the work of turning wheels and lifting weights, but noticed an unavoidable waste in the process. No engine, no matter how carefully crafted, could convert all its input heat into work. There was always a leftover portion, a loss, seeping away as warmth rather than directed motion. Carnot's careful notebooks captured the earliest hints that nature had strict rules about how energy could be organized and harnessed. Shortly after Carnot, another meticulous thinker, Rudolf Clausius, stepped into the picture. By the mid-1800s, Clausius was exploring why energy, though always conserved, seemed to decay into less useful forms as machines ran, and why no magical, frictionless device could ever be built to beat this fate. In 1850, Clausius formalized a principle that would become a pillar of modern physics. Energy naturally flows from hot objects to cold ones, never the reverse, unless outside work is performed. In 1865, seeking a universal language for this phenomenon, Clausius coined the term entropy and gave it a mathematical definition, writing that the energy of the universe is constant. The entropy of the universe tends towards a maximum. For Clausius, entropy was an accounting tool, a way to keep track of every bit of unavailable energy as systems shuffled heat from here to there, always increasing the hidden randomness beneath the observable world. But the plot thickened with the arrival of Ludwig Boltzmann. Living and working in Vienna later that century, Boltzmann recognized the statistical nature underlying Clausius's new law. He saw that heat wasn't a substance, but rather the collective, chaotic motion of trillions of particles. With extraordinary creativity, Boltzmann described how entropy measured the number of microscopic arrangements, microstates, that could produce the same visible, large-scale, macroscopic condition. The more ways atoms could shuffle, the higher the entropy. His insight, S equals sign K log W, remains one of physics' most profound equations, gracing his gravestone as a testament to a lifetime spent mapping the invisible tides of probability. The emergence of entropy didn't happen overnight. Clausius's and Boltzmann's work faced both skepticism and, at times, anguish from a world not yet ready to leave behind certainty for the probabilistic truth lurking under the surface. Boltzmann, in particular, suffered from the philosophical implications of his ideas. If the universe tends towards disorder, does meaning slip away? Or does science hand us a lantern, a way to appreciate order, chance, and structure all the more deeply for understanding their fleeting rarity? Another essential figure, James Clerk Maxwell, introduced thought experiments like Maxwell's demon, challenging and clarifying how information, order, and energy interplay with entropy's laws. Maxwell's demon, that curious imaginary being who sorts molecules in an attempt to reverse the flow of heat, showed that creating order requires effort, knowledge, or an external price, deepening our understanding of entropy and the limitations it places on reality. By the dawn of the 20th century, this trio of thinkers, Carnot, Clausius, and Boltzmann, had planted the intellectual seeds that allowed physics to bloom and branch into quantum theory, statistical mechanics, and even information theory. Their patient interrogations helped dethrone the myth of perpetual motion and forced a reckoning with nature's most trustworthy rules. That heat always flows away, differences always even out, and the universe, step by step, moves from order toward more intricate, probable disorder. Entropy, then, wasn't born from a flash of inspiration. It solidified out of decades of incremental clarity. It was hammered out in the smoky backrooms of European universities, amid the heat of industrial engines, and through the restless calculations of lonely nights. Its emergence marks a triumph of both imagination and patience, a crowning moment in the ongoing quest to write clear laws for the most mysterious flows of nature. Tonight, as you tuck yourself into the restful rhythm of your own routine, you carry with you the legacy of Carnot's engines, Clausius's equations, and Boltzmann's probabilities. Their journey was not just toward understanding entropy, but toward a deeper appreciation of the subtle structures, fleeting yet fundamental, that underpin everything from sunrise to sunset, from the spinning of the earth to the tiny vibrations in your own heartbeat. The emergence of entropy in science is, quietly, the emergence of modern understanding itself. The second law of thermodynamics is one of the great pillars of modern science, an unwavering rule that, like the gentle tug of gravity or the constancy of the speed of light, underpins all the processes that move, change, and animate our world. It's through the second law that entropy finds its lasting voice, shaping not just the fate of engines or the outcome of chemical reactions, but the flow of time itself. As you listen tonight, drifting between wakefulness and rest, consider how this quiet cosmic rule gently but firmly shapes the world you know. So what does the second law actually say? In its essence, the law tells us that in a closed or isolated system, one where nothing enters or leaves, the total entropy can never decrease. In simpler words, left alone, things don't spontaneously organize themselves, but rather spread out, diffuse, and mix. The law can wear many different faces depending on the setting. For a cooling cup of tea, a glowing star, or an aging battery, the details change, but the direction remains. The universe consistently, predictably moves from lower to higher entropy. Let's illustrate this with a memory from everyday life. Think of lighting a candle in a dark room. The wax melts, the flame flickers and dances. Heat radiates out in every direction. Once the candle has burned down, it's impossible for the melted wax to leap back up, unburn and reform the wick, to recapture the heat and light, to reassemble itself in perfect readiness for another spark. This irreversibility is not a failure of design, but a reflection of the second law. The energy released has scattered. The order that once existed has shifted toward a more disordered, more probable arrangement, and entropy has increased. The beauty of the second law is that it explains not just heat and engines, but almost every irreversible change you witness. If you mix cream into coffee, the swirling patterns quickly settle into a uniform blend. If you drop a glass, it shatters. The molecules, the energy, and the components disperse and mix, and there are so many more ways for them to be spread out, and therefore for you to see a uniform drink or a scattered mess, than there are to be gathered, concentrated, and pristine. The law holds true over seconds and millennia, from the life and death of stars to the steady weathering of ancient stones. In scientific terms, the second law imposes an arrow on time. It points only one way. Unlike the first law of thermodynamics, which tells us that energy is always conserved, the second law tells us about the form and quality of that energy. High-quality energy, like that tightly stored in chemical bonds or a compressed spring, is useful and organized, able to perform work. But as it is used and transformed, some always leaks away into less useful forms. Heat loss, friction, the background hum of molecules, where it cannot be gathered up for work again. The second law assures us that no engine or process can be perfectly efficient, because a little entropy is always produced. Physicists have found many ways to phrase the second law, each illuminating a different aspect of its reach. Clausius himself wrote, "Heat can never pass from a colder to a hotter body without some other change, connected therewith, occurring at the same time." Lord Kelvin, another pioneer, pronounced that it is impossible by means of inanimate material agency to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects. Each version sings the same tune. Energy moves from the concentrated to the diffuse, irreversibly, and disorder always edges out order in the long run. This might sound a touch melancholy, but it is also the source of endless wonder. Without the second law, nothing would change, nothing would age, and nothing new could ever arise. There would be no distinctions between past and future, no stories, no progress, and no possibilities. It's because entropy always increases that snowflakes melt, that seeds sprout and grow, that galaxies spin and evolve, and that you, tonight, experience the passing of one peaceful moment into the next. Even on cosmic scales, the second law rules. As stars burn and galaxies collide, their energy spreads wider and wider, raising the entropy of the universe ever higher. Black holes themselves, mysterious and fearsome, are described as the ultimate containers of entropy, holding vast amounts in their invisible interiors, so much so that the surface area of a black hole's event horizon is now understood to be directly proportional to its entropy, a discovery that intertwined thermodynamics, gravity, and quantum theory in a breathtaking leap of imagination. In your own life, you see the second law in the slow cooling of a baked pie, in the wrinkling of a shirt, in the fading fragrance of a flower. Each is an ongoing, gentle nod to the deeper statistical reality that underlies your tangible world. Change comes, but always with a cost paid in new, increased disorder. So tonight, as you settle further into comfortable silence, know that the second law moves with you, surrounds you, connects you to every change from sunset to stardust. Its truth is threaded through physics and chemistry, life and death, and the ordinary and extraordinary alike, always quietly, patiently, and irrevocably setting the direction for all the unfolding transformations in nature's peaceful, relentless tapestry. Nature never runs backwards. This simple phrase arises directly from the profound implications of entropy and the Second Law of Thermodynamics, offering both a scientific anchor and a subtle, deeply intuitive explanation for the way time gently sweeps the world onward, never returning a moment or a molecule precisely to its earlier state. Imagine the small, ordinary events of a quiet day. A glass slips from your hands, shattering on the kitchen floor. The pieces splay outward, scattering with a crisp, chaotic symmetry. Even as you kneel later to pick up the fragments, you might feel a secret certainty that no amount of patience or skill could ever return that glass, atom by atom, to its pristine form. You could carefully glue large shards together, but the microscopic cracks, dust, and lost splinters make the perfect reversal impossible. This irreversibility, so obvious in our daily experience, is a material shadow of entropy's fundamental direction. From a physical standpoint, all of the forces and interactions that govern individual particles, gravity, electromagnetism, and even the quantum rules, are technically reversible. They do not themselves forbid time from running in reverse. If you could film a single billiard ball colliding with another and played it backwards, the laws of physics would look unchanged. Every action could, in theory, be undone. But when you look at many particles together, trillions upon trillions in a warm room, a flowing river, or the atmosphere, something remarkable emerges. The probabilities overwhelmingly favor a forward march from less probable arrangements, order, to vastly more probable ones, disorder. Why is this so? Picture pouring cream into coffee. You watch the elegant curling swirls as two distinct fluids mix. Eventually, the mixture settles into a uniform tan. The original states are gone, replaced by new possibilities at the microscopic scale. While no law explicitly forbids the molecules from unmixing themselves, the chance that every cream particle would spontaneously leap up and rejoin its unblended fellows is so fantastically rare that for all practical purposes, it never happens. There are exponentially more microscopic ways for the cream and coffee to be mixed than separated. Nature simply explores all available options, and the odds always point toward greater mixing, never precise unmixing. This universal drive supplies time's arrow, pointing forever onward. Entropy is that arrow's quiet architect. As entropy increases, the future unfolds, while the past slips quietly into memory. Ordered, detailed arrangements morphing gently into complexity and chaos. Every melting ice cube, every rising tide, every rusting beam follows this same irreversible course. There's no magic spell or physical trick that sends a house of cards to standing after it's tumbled, or flowers to unwither back to bud. In larger arenas, this truth shapes the grandest events in the cosmos. Stars slowly exhaust their nuclear fuel, never naturally reabsorbing their spent energy and shining anew. Mountain ranges weather and crumble. River deltas fan out, never snapping back upstream. Even the elegant spiral of our galaxy carries the imprint of this one-way journey, as its stars orbit, collide, and scatter over eons, ever increasing the entropy of the cosmos. Interestingly, while the core laws at the particle level are reversible, the presence of so many particles and so many possible microstates makes irreversibility our everyday reality and destiny. As Ludwig Boltzmann, one of entropy's greatest explorers, so poetically revealed, the order we see is fleeting and improbable. Disorder, even in all the mathematical anonymity of randomness, is the most probable of all. But does this mean that order never appears? That spontaneity and beauty are doomed to vanish? Not at all. Order arises constantly. Sunflowers bloom, crystals form, music is written and played. But each creation of localized order comes at a price. Somewhere else, entropy in the wider environment increases to balance the equation. Freezers can refreeze water into ice, but only by expelling even more heat into the kitchen. Complex structures and living organisms persist, but only while energy flows from sun to earth, from food to motion, and always in the grand tally, increasing the universe's overall entropy. So, as you reflect on your own memories, the moments you cherish, the meals you've shared, the small wonders you've watched unfold, remember that the reason you remember it all The reason days differ from nights and stories unfold chapter by chapter is that nature never runs backwards. Entropy ensures that each instant is both a continuation and a departure, and that life's gentle current always flows from what was to what will be. Let this realization bring a little comfort as you drift towards sleep, knowing that time's arrow carries you gently forward. The past is securely ordered and set, the present alive with transformation, and the future awaits, shaped by the vast, impartial probabilities that every grain of entropy quietly inscribes upon the universe. Everyday entropy is a presence as constant and familiar as the ticking of a clock or the slow drift of daylight through a window. You may not see entropy at work, but moment by moment, its touch guides nearly every process around you. This invisible tide gently shapes the world you inhabit, from the simplest glass of ice water to the most subtle, gradual changes in a quiet home over the years. Let's start with the way ice melts in a drink. When you drop a cool, hard cube into a glass of juice or water, the cold slowly fades into the drink, and the cube's sharp edges melt away until only droplets remain. What's happening beneath the surface is a beautiful example of entropy's influence. The heat from the liquid flows into the colder ice cube because, at the molecular level, there are many more ways for the combined system to distribute that energy when everything is mixed and matched, water molecules jostling, vibrations evening out, than when the energies are confined to perfectly separate blocks of hot and cold. The process only stops when everything settles at the same temperature, a gentle and final equilibrium, and the possibilities for energy arrangement are maximized. Or consider your morning ritual of making coffee or tea. The mug is hot at first, the aroma rising in gentle curls, but left unattended, the temperature fades. This is not simply a matter of cooling down, but of entropy guiding energy from a place where it's dense and ordered, the hot drink, into the cooler, less concentrated air. The process is slow, but unstoppable, a quiet migration that moves in one direction only. There is no moment, no matter how long you wait, when the cooler air will suddenly leap back into the mug and reheat your coffee. The distribution of energy has reached a new state, more probable because energy is now shared among vastly more molecules. Look around your own living space and entropy lives there too, not as a curse, but as an impartial force behind so many familiar scenes. A loaf of bread left on the counter slowly turns stale. The crispy crust softens, the inside dries, and over time even the flavor and fragrance grow faint. On the smallest scales, water evaporates, molecules escaping from an organized state into the wider randomness of the air. Objects decay and colors fade when exposed to sunlight. Paper yellows, photographs lose their vibrant hues, and fabrics fray. The order present in their chemical structures and pigments is gradually broken down by the energy of sunlight and the small, never-ending movements of atoms and molecules. More mixings, more possible arrangements, more entropy. You might notice entropy in the way your home drifts imperceptibly from order into gentle disorder. A cluttered table, a sock that never quite finds its matching pair, books leaning on one another after being browsed and moved. The more ways these familiar things can be jumbled, the higher the entropy of the scene. Restoring order, a clean, organized room, always takes effort, a little input of energy, because it means actively working against the dominant trend. Even the humble process of cooking is led by entropy. Heat moves into a pan, changing raw batter to a golden fluffy pancake or a smooth egg to a solid one. During baking or frying, molecules within the food react in countless ways, new bonds forming, old ones breaking. The final meal represents a new arrangement, a lowering of local order, and an increase in the disorder of the wider environment as heat and aroma drift outward. These little moments, melting, cooling, fading, staling, might at first seem melancholic. Yet entropy is not a thief of beauty or potential. It's a reminder that change is relentless, but also creative. New flavors arise, aromas fill a kitchen. The warmth from tea moves gently through the room, caressing the air you breathe. Even the gentle exhaustion you feel after a day's work is partly entropy's doing. When your muscles contract, they turn chemical energy into movement, which quickly becomes warmth lost to the world. The heat you radiate is the final soft signature of body and mind finding rest. The tidy chemical stores you began the day with have dispersed into more probable, less organized forms. Entropy gives rise to the comfort you feel curled under a blanket, the softness of sheets, the coziness of warmth mingling with the cool night air. Every shared laugh that makes a room vibrate, every soft echo that fades into silence, is part of the ongoing tendency for order to blend into greater complexity, greater possibility. So as you pass through your day and find yourself quietly observing how things change, how the fresh, the hot, the new gently fade toward balance and equilibrium, let yourself find a kind of reassurance in the universality of entropy's influence. You live not in defiance of this rule, but in harmony with it, moving through a world where every act of mixing, melting, cooling, and resting is both an end and a beginning, a tiny echo of the greater unfolding and rebalancing that happens throughout the known universe. Entropy and your body are bound together in a finely tuned dance, one so intimate and continual that every beat of your heart, every blink of your eye, and every breath you take is shaped by the silent arithmetic of this universal law. Even now, as you relax and prepare for rest, your living self is a temporary but extraordinary outpost of low entropy, working quietly against the natural drift toward disorder, but always, inevitably, a participant in entropy's gentle increasing tide. Consider first each breath you draw in. Oxygen moves from the air to your lungs, diffuses into your bloodstream, and gets whisked to your cells, where it is used to transform food into usable energy. This entire process is an exquisite example of order, carefully regulated steps built by evolution to keep your chemistry working, moment to moment. Yet, as efficient as this machinery is, each useful transformation is accompanied by a little bit of wasted energy, released as heat, and a shifting of molecules toward more probable, more randomly distributed states. You radiate warmth, not just because of the weather, but because your body is always giving up a little order, raising the entropy of your surroundings, just to power its daily miracles. Each cell within you works tirelessly to maintain its own structure. The thin membranes of your cells actively pump ions to keep concentrations just right. Enzymes build and break molecules as needed, and the bustling citizenship of proteins, lipids, and sugars keep each molecular assembly in place. This isn't done for free. It demands a constant input of energy you get from food, which in turn comes from plants that gathered sunlight, themselves organizing a flood of photons into precise chemical patterns. Even at rest, your body expends energy to sustain order, regulating temperature, repairing minor damage, synthesizing molecules, and clearing away the waste left behind by cellular activity. But entropy's lesson for living things runs deeper still. All life at every level is a subtle balancing act, a local reversal of entropy accomplished by spending energy, always at the cost of increasing disorder somewhere else. This is why you eat multiple times a day, why you need water, why living things are always energy consumers. Take the metaphor of a refrigerator. Inside, things become cold and orderly, but only because the machine works to push heat outward into your kitchen. The net effect, when you count both the inside and the outside, is still an increase of entropy. The same is true with your body. Wherever you marshal molecules into structure and function, the wider world becomes just a little more random. Tiny as your cells are, their battle against disorder is astonishingly persistent. DNA, the blueprint of your being, is under constant attack by entropy in the form of chemical decay and molecular error. Complex repair enzymes monitor and fix mistakes, using even more energy to briefly postpone disorder. But over years and decades, small degradations accumulate. Errors slip through the net, and the exquisite order of your body slowly unwinds. This is why aging exists. Wrinkles, grey hair, slowed healing, the subtle loss of vigor, all are quiet signatures of entropy gradually overtaking the intricate low-entropy patterns that defined your youth. Heat production is another expression of this endless dance. The warm glow of your skin, felt by a loved one or a pet snuggled beside you, is the radiant side effect of every bodily process. You cannot convert all the stored energy from food into movement or thought. Some must always escape as heat, raising the entropy of your surroundings. In sleep, your body's systems slow but never stop. The ticking over of your metabolism continues to swap order for increased chaos in the outside world, the exchange as gentle and constant as the flow of a quiet stream. Yet the presence of entropy in your body is not a source of despair, but a testament to life's remarkable ingenuity. All living things are masters of channeling energy, shaping fleeting islands of order within a rushing sea of disorder. Plants assemble sugar from sunlight and air. Animals build muscle, bone, memory, and imagination. Even the smallest bacterium secures its structure for a bit, holding entropy at bay if only temporarily. Your very thoughts, the tranquil currents of your dreams, are possible because biological order is actively generated and preserved, staving off chaos long enough for consciousness to emerge. If you look outward, you'll see mirrors of this process in the world of technology and society. Cities, machines, books, languages, each is an enclave of pattern, maintained with the tireless input of energy and attention, destined to fade unless supported by further effort. And so it is too with life. Islands of order, sustained at the expense of greater disorder elsewhere. So as you rest tonight, know that your comfort, warmth, and gentle pulse are the living testament to entropy's role in the body. The world outside your window grows ever more disordered as you maintain your own fleeting balance. And when you finally slip into sleep, your body continues its quiet resistance, a celebration of life's extraordinary, temporary victory over the calm and patient rise of entropy. Entropy, stars, and the universe are woven together in one vast story, a cosmic epic that stretches from the fiery birth of the first atoms to the quiet, ever-expanding chill of space. As you sink deeper into the hush of the evening, try to imagine the scale at which entropy rules, guiding not just the melting of ice in a glass or the gentle fatigue of your body, but the creation, life, and eventual death of stars, galaxies, and perhaps reality itself. Let us begin billions of years ago, in the hot, condensed moments just after the Big Bang, a universe of unimaginable density and simplicity. At that moment, all of space and energy was packed tightly together, an initial condition of remarkably low entropy, where there were relatively few ways to arrange all the matter and energy compared to what would follow. Out of this ordered beginning, the universe began to expand and cool. Space unfolded, and with each tick of the cosmic clock, entropy increased, opening up more possible arrangements for matter and energy to spread, mix, and evolve. As the universe expanded, some regions were a little denser than others, thanks to minute fluctuations in the primordial soup of particles. Gravity quietly magnified these tiny differences, drawing matter together to form clouds, then stars, galaxies, and clusters, a process that, paradoxically, increases the universe's overall entropy even as it creates new cosmic structures. How is this possible? When gravity clumps matter together, like in the birth of a star, it liberates enormous amounts of energy as heat and light, which radiate outward, vastly increasing the number of ways energy is spread through space. In this sense, every newborn star is a pyre of growing entropy, shining because of energy's dispersal. Consider the life of a star, like our own sun. Deep in its core, immense pressure and temperature allow nuclear fusion to take place, forging lighter elements like hydrogen into heavier ones, helium, carbon, oxygen. Each fusion reaction converts a bit of the sun's mass into pure energy, a process described by Einstein's famous equation, E = mc2. The energy produced doesn't stay hidden. It travels outward as radiant light and heat, eventually reaching the coldness of space and sometimes the tender leaves of a plant on Earth. This outpouring is entropy's work. Each photon cast away is energy spread, a step further from concentrated fuel toward the gentle uniformity of the dark, expanding universe. Yet the story of stars and entropy is not one only of creation, but also of inevitable transformation. A star, having exhausted its primary fuel, cannot maintain its ordered, burning core forever. The fate of the star depends on its mass. Small stars gently fade, becoming white dwarfs and eventually, after unimaginable spans, black dwarfs. Stars many times the size of our Sun end in dramatic explosions called supernovae, scattering their heavy elements, carbon, iron, gold, into space, seeding new generations of stars and planets. Each step sees energy released, matter distributed, and entropy increased. Black holes, among the most mysterious of celestial objects, are perhaps the universe's ultimate storehouses of entropy. When a massive star collapses into a black hole, it concentrates mass in a tiny region. But the entropy involves skyrockets. The event horizon of a black hole, the cloak beyond which nothing returns, holds an enormous amount of entropy, described by its surface area rather than its volume, a surprising result first proposed by Stephen Hawking and Jacob Bekenstein in the 1970s. This insight bridged thermodynamics with quantum physics and general relativity, hinting at a deeper link between information, entropy, and the very shape of space-time. Even on grand scales, entropy remains relentless. Galaxies spin, collide, and merge, their stars flung into new orbits or swallowed by expanding darkness. Over unimaginable eons, fuel runs out, stars die, and the universe's entropy ticks ever upward. The fate of the cosmos itself is tied to this climb. The heat death scenario, contemplated by physicists for over a century, envisions a future where all useful energy is spent, matter decays, and everything is spread thin across an ever colder, darker sky. In this final act, entropy finds its highest expression, not as chaos, but as the perfect uniform sameness with no gradients left to drive change. Yet in this steady march, there is awe and comfort. Entropy's great narrative links you to the stars above, to the gentle warmth that will one night touch another world, and to the heavy elements in your own body, born in the collapse of ancient suns. These cycles, unhurried and unbroken, reveal how the patient work of entropy makes room for creativity, order, and possibility, even while softly insisting on the universe's ultimate destiny. So tonight, as you peer out your window, or simply let your mind wander among the stars, remember, entropy is the engine behind their light, the author of their fate, and the principle that, in ways both tender and profound, connects every atom in your body to the distant whispering edge of the cosmos. Thermodynamic equilibrium is where entropy finds one of its most peaceful and final expressions, a kind of serene settling where the wild currents of flow and change subside, and all things within a system reach a tranquil sameness. This concept weaves quietly through the science of heat, chemistry, and the ceaseless balancing acts that underwrite everything from the weather in your city to the softness of your bed. So, what exactly is thermodynamic equilibrium? Picture a mug of hot tea placed in a cool, quiet room. At first, the tea steams and the air above shimmers with rising heat. The molecules in your drink jostle and vibrate faster than those in the surrounding air, brimming with thermal energy. But as time slips by, heat leaks gently into the air, the cup becomes less warm, and the steam thins and vanishes. Eventually there comes a calm moment when the tea, the mug, the air, even the table beneath, all reach exactly the same temperature. Nothing more flows from one part to another. This is thermodynamic equilibrium. It is the grand evening out, when no energy can be transferred as heat between any part of the system. Entropy has climbed to its maximum possible value for this scenario, and no further spontaneous changes can occur within its boundaries. In science, equilibrium is not only about temperature, it's about balance in all things. Temperature, pressure, chemical potential, and the concentration of substances. Consider this as you cook, when salt is stirred into soup. At first, the concentration of salt is high where the crystals land, but as you stir, the salt disperses. Eventually, every spoonful you taste is equally seasoned. No matter how long you wait, the salt never rushes back to its starting corner. The distribution has smoothed itself out into equilibrium, a state of maximum entropy for the soup. The journey to equilibrium is always a journey toward greater entropy. Every gradient, a difference in heat, pressure, or concentration, serves as an opportunity for energy or matter to spread out and blend. The flow ceases when all gradients disappear, when everything is perfectly mixed and matched. This is true no matter the scale or setting. from the deepest ocean currents reaching for balance with the sky, to the tiny, invisible shuffle of ions inside your own cells. On the smallest scales, equilibrium can happen blindingly fast. Gases in a closed container will even out their energies and densities in microseconds. Inside your body, blood moves, oxygen and carbon dioxide swap places in the lungs, and countless ions shuffle during each heartbeat, all seeking their local equilibria. On the largest scales, whole planets and stars evolve toward balance, molten rock hardening into crust, the fierce nuclear fires of suns burning until their fuel is spent and their light flickers out. But not all systems ever truly reach equilibrium in practice. Life itself is a grand exception, constantly importing energy to stave off the final, restful equality that marks true equilibrium. Living things are always slightly out of balance, always using energy to build, move, signal, and repair. As soon as this process stops, when the external energy supply is exhausted, the march to equilibrium resumes, and the entropy of the system suddenly jumps. This is why equilibrium, while beautifully restful, is often at odds with vitality and change. It's reassuring, though, to realize how equilibrium plays out in daily life. When you find comfort in a sun-warmed room, it's because the air has reached evenness, no longer pushing cold drafts into warm corners. Your refrigerator labors to keep one part of your kitchen a little bit out of equilibrium, pulling warmth out to ensure freshness within. The gentle hum you hear as it runs, or the warmth on its outer surface, is the footprint of entropy increasing as the machine pulls off this bit of local order. Chemistry, too, is deeply governed by the principle of equilibrium. Any chemical reaction, left to itself, will flow toward a point where the forward and reverse processes balance, where reactants become products at the same rate that products revert to reactants. At equilibrium, concentrations remain constant, and the system's entropy cannot spontaneously climb higher without changes from the outside. This is why soap bubbles shrink down to the smallest, roundest shapes, why perfumes fill a room, why water pours itself evenly through the loops of a garden hose. In the universe at large, equilibrium is a rare state, one not often reached but always approached. The cosmic background glow we see across the whole sky, faint and ancient, is the signature of the early universe finding a kind of equilibrium long ago, a gentle sameness left behind as galaxies and stars began to grow out of the cooling chaos. So as you feel the even warmth of your blankets tonight, or remember the peaceful hush when a storm outside finally settles, know that you're experiencing the calm endpoint entropy seeks within any system. Equilibrium is not a defeat or a loss, but a natural, patient blending where all possibilities are fully explored and chance itself finds rest. It's the lullaby at the end of every energetic day, the quiet exhalation as all things for a moment find their gentle, most probable place. Measuring entropy may seem like trying to catch mist with your hands. How can one assign numbers to something so invisible, so woven into the secret arrangements of particles and probabilities? Yet, over generations, scientists have learned not only to define entropy with clarity, but to measure it with remarkable precision, allowing us to chart its subtle increase in everything from a burning log to the cooling of a cup of tea. This act of measurement transforms entropy from an abstract notion to a practical, indispensable tool in physics, chemistry, engineering, and even information science. Let's begin gently with the fundamental idea that entropy quantifies the number of microscopic ways the particles in a system, atoms, molecules, even photons, can be arranged while still presenting the same outward or macroscopic appearance. Recall Boltzmann's famous equation, S equals sign K log W. Here, S stands for entropy, K is Boltzmann's constant, about 1.38 x 10 circumflex 23 joules per Kelvin, and W is the number of microstates, the parallel universes of positions and speeds that would seem on the surface indistinguishable to you or me. In practical terms, if you have a box of gas, W counts every possible way the molecules could be distributed, flying at different speeds and angles, yet still maintaining the same pressure and temperature overall. The formula's logarithmic nature adds an elegant twist. Even small increases in how many ways particles can be arranged reflect as steady, predictable increases in entropy. Why logarithms? Because as the number of microstates grows exponentially with more particles and energy levels, the log function tames this explosion, making entropy changes manageable, measurable, and linear on the scales we encounter daily. Now, how do scientists actually measure this invisible property? Historically, the first approach was thermodynamic. Clausius showed that if you add a precise quantity of heat, Q, to a system at a constant, unchanging temperature, T, the change in entropy, S, is simply S equals sine Q, T. This allows you to calculate, for example, the entropy gained when ice melts at 0 degrees Celsius by measuring the heat absorbed by the ice and dividing by the temperature in kelvins. Each small, exact transfer of energy is accompanied by a precise tick on the entropy meter, so to speak. Modern laboratories use a wide range of clever instruments to measure entropy and its changes. Calorimeters quantify how much heat is gained or lost, from oils in an engine to cells in a living body. Pressure gauges, thermocouples, and spectrometers record the behavior of gases, liquids, and solids under different conditions, letting scientists determine changes in entropy even when direct counting of microstates is out of reach. Entropy doesn't always deal in enormous numbers. It is just as handy for the very small. In chemical reactions, the entropy change can be calculated using tables called standard molar entropy values, which are carefully compiled for thousands of pure substances. When you mix chemicals in a beaker, these tables, backed by generations of careful calorimetry and analysis, allow chemists to predict whether a reaction will want to proceed and how much more dispersed the energy and matter will be afterwards. One breathtaking example of entropy's measurement is found in black holes. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking deduced that the entropy of a black hole is proportional to the area of its event horizon, not its volume, a fact confirmed by indirect calculations from gravitational wave measurements and astronomical observations. Amazingly, by plugging in the physical constants, Planck's constant, the speed of light, Newton's constant, and Boltzmann's constant, they proved that black holes possess mind-bogglingly large entropy values, far higher than anything we encounter in daily life. In information theory, entropy measurement takes a fascinating turn. Here, the particles are possible messages or data strings, and entropy quantifies uncertainty. Claude Shannon defined the entropy of a message as a sum involving the probability of every possible symbol or word, using the same sort of logarithmic function that Boltzmann did for molecules. In both worlds, entropy counts the possibilities. The higher the entropy, the greater the surprise, variety, or hidden randomness. For perspective, the entropy of melting 1 kilogram of ice at 0 degrees Celsius is about 1,200 joules per Kelvin, a tidy number that lets engineers and scientists calculate everything from power plant efficiency to the design of delicate pharmaceuticals. In a more everyday context, the entropy produced when you burn a single match is enough, in theory, to drive billions upon billions of molecular rearrangements in the surrounding air. And in the minute machinery of life, careful measurement of entropy allows biochemists to track changes in order and disorder as tiny reactions unfold in your cells. The slight rise in entropy when oxygen binds to hemoglobin, or when a protein folds into its functional shape, can be charted and understood. So, next time you touch a warm mug, see frost fading from a window, or receive a digital photo across the world, remember, behind all this is a subtle tally of possibilities, measured with silent accuracy. The science of entropy's measurement is an ongoing triumph, one that transforms an invisible cosmic accountant into a trusted companion of every scientist, quietly recording the inevitable flow from less to more, from ordered to probable, as our world turns and time gently strides ever onward. Surprising examples of entropy can be found woven throughout your days and nights, hiding in humble scenes and astonishing extremes alike. Though often described as an abstract or distant principle, entropy softly touches the familiar and spectacular, connecting the mess of a sock drawer with the cosmic mysteries of the universe. These examples show that entropy is not only a mathematical curiosity, but a presence at every scale of existence, gently shaping both the ordinary and the unimaginable. Let's begin at home, in the comforting clutter of a drawer. When socks are freshly laundered and paired, the system is highly ordered. There are only a few ways to arrange perfectly matched pairs. But as time passes, socks are worn, returned, maybe lost behind the dryer and tossed back in without care. Far more arrangements, millions more, fit this new jumbled state than the original ordered one. Each session of rummaging increases entropy, with every missing mate expanding the number of possible drawer configurations. This mundane shuffle is entropy at play, not a force acting directly, but the natural likelihood of all the ways disorder can arise, outweighing those rare ordered possibilities. Now let's wander to the world of puzzles. If you drop the pieces of a jigsaw puzzle onto a tabletop, the chance that they might land already assembled is astronomically low. There are countless combinations that produce a mess, but only one way that reveals the intended picture. Solving the puzzle, you invest energy, attention, and care, creating local order. But the wider world pays the price, as heat from your brain and body disperses into the room, balancing the increase in order with a rise in overall entropy. Move, for a moment, to the swirling sky above. A campfire releases aromatic smoke into the evening air, painting pale, curling trails. At first the smoke forms visible patterns, but as minutes pass, it diffuses until it has mixed with the whole atmosphere, its molecules scattered so widely that the original shape vanishes. Entropy here is the spread, the mixing, the ceaseless tend toward randomness. The same principle explains why scents fill a room, or steam rises from soup and fades into memory. Yet entropy's reach is not limited to earthly scenes. Perhaps the most dramatic example comes from the enigmatic realm of black holes. As stars collapse under their own gravity, the matter inside is squeezed ever tighter until it passes beyond the event horizon, becoming inaccessible to the outside universe. When Jacob Bekenstein and Stephen Hawking studied these regions, they made a breathtaking discovery. A black hole's entropy is not related to how much it contains, but to the surface area of its event horizon. This means black holes possess unimaginably high entropy, more than the rest of the universe put together in some cases. Each bit of matter or light that falls in adds to this entropy, making black holes the densest information vaults in the cosmos. In chemistry, entropy's surprising effects can appear as spontaneous reactions or as barriers to ones that should, by energy alone, seem easy. Some substances dissolve readily in water because their molecules have more possible ways to distribute and move afterward. Entropy's gentle favor for variety paving the path. In contrast, making a supersaturated solution, or coaxing a crystal to grow, takes careful manipulation, fighting entropy's preference for mixing and dispersal. Musicians, too, encounter entropy in a quiet way each time they tune their instruments. Perfectly tuned strings or pipes represent rare, organized energy states. As they're played, vibrations slowly lose their energy to the wood, the air, even the hands, a diffusion of motion and sound that increases entropy, turning sharp notes into soft echoes and finally into silence broken only by memory. In geology, mountains rise through titanic effort, pushed upward by the collision of plates and the slow, persistent flow of rock. Yet over millions of years, wind, rain, and glaciers grind them down, returning their order to the gentle spread of silt and clay, entropy turning grandeur into the approachable, the small, the even. Computers and data centers face entropy's hand too. Magnetic disks, microchips, and flash drives are marvels of organized information. Over time, cosmic rays, heat, and electrical noise create tiny errors that, left unchecked, erase or scramble stored data. Massive systems are put in place to correct these errors: error detection and correction, redundant drives, energy-hungry cooling. Each effort paying for temporary order with the greater entropy and heat released into the environment. Finally, let's turn to one of the most extravagant expressions of entropy, the cosmic microwave background. This faint glow, visible only to sensitive instruments, fills the universe as a relic of a time almost 14 billion years ago, when everything was smoother, simpler, low in entropy by today's standards. Over eons, as matter clumped and stars burned, energy has spread outward, cooling the sky and lifting entropy to heights unimaginable at the dawn of time. These examples, socks and smoke, puzzles and black holes, music and mountains, data and distant starlight, encourage us to see entropy not as a threat, but as the gentle logic that links every scale of reality. The odds quietly guide all things toward greater possibility, more ways to be, weaving both the common and the cosmic into a tapestry of restless, creative change. Entropy in chemistry is the quiet arbiter of reaction paths, gently directing which transformations can occur naturally and which demand extra intervention. Each time molecules interact, mixing, reacting, exploding, dissolving, entropy stands as the patient accountant, tallying up how the possibilities for arrangement, energy and movement shift before, during, and after every process. This silent judgment explains not only why some reactions proceed spontaneously while others resist, but also why certain familiar reversals, such as unmixing, unbaking, or unscrambling, simply never occur. Let's slip into the microscopic world of a beaker filled with water, into which you sprinkle a spoonful of sugar. At first, the sugar crystals are neatly ordered, but once in water, their constituent molecules scatter and diffuse, tumbling into countless arrangements, so that after a short while, the entire solution tastes sweet. This mixing is not favored simply because nature likes disorder, but because there are exponentially more ways for the sugar and water molecules to be intermingled than to remain in their neat, original forms. Entropy here measures the leap in statistical possibility from order to a rich diversity of outcomes. In chemical reactions, entropy helps decide which paths are open and which are closed. Consider the classic case of rust. Iron exposed to air combines with oxygen, forming flaky orange-red iron oxide. The initial state, metallic iron and gaseous oxygen, is quite orderly, but as they react and bind into rust, the products have a larger number of ways to arrange themselves. Even if this process requires a local energy input to get started, it is entropy's increase, more possible configurations, more randomness, that drives the reaction forward. The reverse, rust spontaneously becoming fresh iron and oxygen gas, is so unlikely that we simply never see it in practice. This theme appears again and again. When a substance burns, such as a log in a fireplace, the carbon, hydrogen, and oxygen atoms rearrange, creating gases and heat. The heat flows into the surrounding air, and the number of microstates for all these molecules skyrockets. The smoke drifts and disperses, as does the energy, entropy increasing relentlessly at each stage. If you could somehow gather up all the heat and smoke, you would find that the smallest increase in entropy renders the process practically irreversible. In a more surprising twist, entropy can help reactions occur even when energy appears to disfavor them. Take the process of dissolving table salt in water. Although energy must be spent to separate the ions from the solid salt, the increase in entropy as ions spread out and water molecules arrange and rearrange themselves drives the process to completion. Entropy grants permission where energy alone may hesitate. Many chemical reactions unfold with a delicate interplay between two great forces: enthalpy, a measure of heat content, often released or absorbed in reactions, and entropy, a measure of possible arrangements and disorder. The free energy equation, written as dg = dH TdS, expresses this balance. dg is the change in free energy, determining if a reaction is spontaneous. dH is the change in enthalpy, heat effects. T is absolute temperature, and ds is the change in entropy. If the increase in disorder, ds, is large enough, it can tip the balance and make a reaction spontaneous, even one that would otherwise seem energetically uphill. Proteins provide a vivid example from biochemistry. When a protein folds into its intricate functional shape, the process appears to decrease entropy locally. The folded molecule is more ordered than its floppy, unfolded state. However, in folding, the surrounding water molecules are freed to explore more arrangements. The net result is still an increase in overall entropy for the entire system. Order is built on the molecular stage, but hidden chaos increases among the water molecules just out of sight. Reactions in living cells are shaped by entropy's steady hand. Metabolic pathways, those intricate networks that digest food, repair cells, or produce energy, rely on stepwise increases in entropy to ensure that waste is expelled, energy is distributed, and molecules are continually renewed. This subtle bias underpins the direction of life itself. Food is digested, not spontaneously reassembled. Dying cells are recycled, not reformed whole. Entropy can also create barriers. Chemists sometimes seek orderly products like precious crystals or pure compounds, but the universe insists, through entropy, that disorder is overwhelmingly likely. Without careful control of temperature and concentration, crystals tend to dissolve and mixtures become indistinct, drawn toward the sprawling randomness that is always statistically favored. Consider, for a surprising finale, the making of a cake. Mix flour, sugar, eggs, and butter and heat them in an oven. A host of chemical reactions take place. Proteins cross-link, starches gel, new flavors and aromas blossom. The resulting cake is more complex, more randomized at the molecular level, and its baking releases heat into the kitchen air. Unbaking this cake, reassembling the raw ingredients and recapturing every joule of warmth, would mean reversing countless, nearly all, increases in entropy. That's why the scent of baking drifts away, never to be fully recovered, and the process is so obviously one way. In sum, entropy in chemistry walks hand in hand with the odds, gently guiding molecules towards more probable configurations, away from neat arrangements and singular possibilities, and into the lush diversity of mixed, balanced, and changed states. This journey is at the very heart of why chemistry works, why life is possible, and why the world continues its subtle, ceaseless transformation, one reaction and one increase in possibility at a time. Information theory and entropy might at first seem to belong to distant worlds, one concerned with the movement of atoms and heat, the other with the flow of messages, codes, and knowledge. Yet, in a remarkable convergence, scientists discovered that the mathematics of entropy binds these realms together, revealing a deep, universal connection between physical disorder and uncertainty in information. In the tranquil quiet of this evening, let's gently wander through the meeting of physics and information and uncover the invisible symmetry that shapes both the digital and the natural worlds. It was in 1948, as radios hummed and the world leaned further into the age of technology, that an American mathematician named Claude Shannon introduced a revolutionary new language for understanding communication. In the infancy of computers and telegraphs, Shannon wondered, how much information can be reliably sent over a noisy channel? What is the true content of a message, given that some of it could be random, garbled, or expected? To answer, Shannon borrowed the concept of entropy from thermodynamics, but adapted its meaning. In his theory, entropy measures the average uncertainty or surprise within a stream of signals, a kind of tally of all the possible things a message could mean, given what's known and unknown. If every letter of a message is perfectly predictable, say, a book filled with only the word hello repeated, then the information entropy is low. But if each letter or word could be anything picked at random from a rich alphabet, the entropy is much higher, reflecting far greater possible content and surprise. Mathematically, he defined information entropy as H equals sign px log 2 px, where EPX is the probability of each symbol or message's appearing. This expression looks uncannily like Boltzmann's equation for thermodynamic entropy, swapping physical states for possible messages and counting in bits, binary choices, rather than molecules. The deeper reason is that both formulas tally up the richness of possibility, whether that possibility is hidden in clouds of gas or lurking in an electronic transmission. Entropy in information theory isn't just an abstract number. It is the guiding principle behind all data compression, encryption, and digital communication. Imagine sending a picture over the internet. If the picture is of a blank blue sky, its entropy is low. Most of the pixels are the same, and the file can be compressed heavily. If the image is a bustling market filled with 100 colors and textures, the entropy is high. Each detail might be unique, and compression becomes more challenging, reflecting the abundance of possible arrangements. Even the simple act of guessing a password is an exercise in entropy. A password of 1234, common and expected, has a lower entropy and is easier for someone to guess. Random combinations like HQ6, ZT8C, have high entropy, a signal of greater uncertainty, and are thus harder to predict or crack. In cybersecurity, quantifying the entropy of keys and codes helps keep secrets safe and data private in a sprawling connected world. But the links between entropy and information run deeper still. The universe's tendency toward higher entropy means, in a sense, that there is always less information or more uncertainty about the precise arrangement of all its pieces, unless one invests energy to sort, measure, or record. This subtle truth is echoed in physics, where the entropy of a system is a measure of what is unknown about the internal details of its state. In the laboratory, the more uncertainty about the positions and momenta of particles, for example, the higher the entropy. Fascinatingly, black holes, once again, provide a place where information theory and physics meet. Stephen Hawking's groundbreaking work showed that black holes, with their immense physical entropy, also represent a profound uncertainty about the information they contain. The famous black hole information paradox asks, is information erased forever when matter falls into a black hole, or does it somehow survive at the edge of the event horizon? The question cuts to the core of both thermodynamics and information theory, and is a lively frontier for physicists and mathematicians even now. In daily life, entropy and information theory underpins technologies that sustain your world. The way your phone compresses voicemail or images to send across the globe, the error-correcting codes that protect your emails from being garbled, and even the advertisements you see, shaped by algorithms that estimate the surprise of your next click. At a deeper level, this principle invites reflection. Your memory, too, is a balancing act of order and uncertainty. Bits of information gained, some details lost, the richness of possibility making each moment both unique and unpredictable. Each conversation, story, or burst of creativity represents a subtle interplay between known order and new, unexpected information. So, as you drift tonight through the mysteries of the seen and unseen, know that entropy is your invisible companion, not just in the warmth of your breath or the spread of sound, but in every bite of information, every shared word or confident silence. Whether counting molecules or possibilities, entropy is the universal measure of the unknown, a quiet, constant pulse beneath both the laws of nature and the messages that make you who you are. Entropy's limits greet us like gentle exceptions along a winding path, a reminder that, while the universe overall trends toward disorder, pockets of order and structure can and do emerge in breathtaking and sometimes counterintuitive ways. Understanding these limits doesn't contradict entropy's rule. Instead, it deepens our appreciation for the complex dances of balance and emergence that shape the natural and human-made worlds. To see this in action, look first at the phenomenon of spontaneous order. In certain situations, systems far from equilibrium can develop structured patterns, beautiful lattices, or even exhibit what looks like a temporary decrease in entropy. Take snowflakes, for example. As water vapor in a wintry cloud cools, its molecules align themselves into the intricate hexagonal symmetry we associate with snow. Each snowflake, unique yet ordered, emerges from randomness. Locally, the forming crystal drops in entropy, molecules arranging themselves just so, but only because the process overall dumps even more disorder as heat into the surrounding air, ensuring the universe's total entropy still grows. Crystals of table salt form sharp, geometrical cubes as salty water evaporates. Soap bubbles often self-organize into shimmering nested shapes, and in crowded ponds, living slime molds or bacterial colonies create crafted patterns that seem to contradict the march to disorder. In all these cases, local decreases in entropy are sustained by energy flowing through the system, sunlight, food, or temperature gradients, that drive continuous change and pattern formation. Such dissipative structures, as Nobel laureate Ilya Prigogine called them, are found across nature. Hurricanes, sand dunes, even the circulation of air in your own kitchen as it cools. Biological systems are the most astonishing examples of order emerging from chaos. A single fertilized egg divides and differentiates into the trillions of specialized cells that compose a human being. all guided by the instructions encoded in DNA and millions of daily energy transactions. Life at every level is a local rebellion against entropy, order maintained moment by moment by the constant import and flow of energy, whether from sunlight and sugar in plants or food and oxygen in animals. These living structures, however, never violate entropy's law. Instead, they temporarily decrease entropy locally by increasing it somewhere else, always with an energy cost. The energy in a green leaf, the order in a honeycomb, or the knowledge locked in a library of books is built by spending down gradients, the warmth of the sun, the calories in a meal, the patience of hands and minds at work. The second law of thermodynamics still reigns. It's just that its effects are distributed across a system and its environment, not always apparent in every corner at every moment. Sometimes, entropy's limits reveal themselves through surprising reversals in systems at small scales. In the laboratory, if you isolate a tiny handful of particles, fluctuations can briefly make order emerge at random, gas molecules clustering together instead of spreading, for instance. But these moments are exceedingly rare and transient, quickly erased by the next shuffle of chance. This microscopic stochastic behavior shows that while the law of rising entropy rules the average behavior of large systems, unusual things can and do happen over tiny spans and spaces, only to be reabsorbed as normal disorder takes over again. Another striking boundary comes from the quantum world. In certain quantum states, matter can seem remarkably ordered. A superconductor, for instance, channels electrons with no resistance, creating ordered patterns that, at first glance, defy ordinary notions of energy loss and entropy. Here, the low entropy state is preserved not by breaking the rules, but by quantum effects and very careful control of temperature and environment. Eventually, unless continual effort is supplied, these states also yield to entropy. On the human level, we harness entropy's limits when we design machines and harness feedback loops. Thermostats, computers, factory lines, all require a flow of energy and a careful balance to maintain order and function. Still, as these systems operate, the total entropy, including the heat and waste generated, continues to increase overall. Importantly, each pattern or patch of order, every cell, crystal, and spiral galaxy arises not in spite of entropy, but because of the energy flows and constraints that shape possibilities in the real world. Our universe is not a uniform swirl of maximum entropy, but a tapestry continually animated by gradients, those differences in temperature, pressure, or concentration that allow order to spring forth, even if only for a while. As you drift further into calm, remember that life's beauty and complexity stand as the most moving testimony to entropy's subtlety, not its tyranny. The spirals on a seashell, the geometry of snow, the structure of your own thoughts, they exist because in a world where total entropy always rises, the rules allow for local islands of order, transient and fragile, but all the more precious for their rarity. Entropic heat death is an idea both sobering and awe-inspiring, hinting at the universe's quiet destiny in the farthest future. This concept, born in the 19th century and evolving through the lens of modern physics, describes a time when entropy has reached its possible peak, when the swirling energy that powers stars and life, storms and seasons, has been so thoroughly spread and diluted that the cosmos falls into a peaceful but inert slumber, a state known as maximum entropy. Let us ease our way through this prospect. The term heat death comes from those early pondering scientists, Rudolf Clausius, William Thomson, better known as Lord Kelvin, and others, who realized that all energy transformations have a cost, a growing cumulative drift toward more probable, less useful arrangements. As stars form, burn and die, as galaxies merge and scatter their contents, as every process radiates heat gently into the black fabric of space, entropy ticks steadily upward. Unlike the vivid, sporadic bursts that define the universe's youth, the aged cosmos is imagined as a realm where every temperature gradient, every chance to extract useful work, has faded away. Over immense timescales, trillions upon trillions of years, stars consume their fuel, grow dim and vanish. The ashes of these stars, the white dwarfs and neutron stars, slowly cool. Black holes too may eventually evaporate through the faint release of Hawking radiation, each quantum of energy carrying a fragment of the universe's information content away. All the while, matter decays, protons perhaps dissolving into radiation over timescales almost impossible to imagine. In this distant epoch, scattered light from the final stars and galaxies has been stretched by the expanding universe, cooled to near absolute zero by endless cosmic inflation. Gas becomes so rarefied and distributed that it cannot collapse to form new suns or planets. The last chemical reactions flicker out, and motion itself becomes a ghostly memory. In such a cosmos, heat, the jostling and vibration of atoms and molecules, can no longer flow from warmer to cooler regions, because everything everywhere has the same, utterly even temperature. There are no more gradients, no more energy imbalances to tap, no more processes that can lower entropy anywhere without raising it elsewhere. The universe at last settles into thermodynamic equilibrium on the broadest possible stage. This heat death is not violent or catastrophic. It is instead an asymptotic approach, a creeping, unstoppable quiet that overtakes not just planets or stars, but the structure of reality itself. It would mean the end of work in the physical sense. No engines to run, no energy to store or release, no structures to build or break. Information itself would be lost amid the vast sameness, and the prospects for memory, life, or renewal would fade to shadows. Yet some physicists offer gentle nuances. Quantum mechanics and subtle new physics still leave room for unknown surprises. The expansion of space and the realm of dark energy may reveal long-term fates yet unimagined. Some scenarios speculate about cycles or new beginnings, others about infinite diffusion. Still, the weight of our best understanding is that entropy's climb leads, inevitably, to a future where everything physical shares the same chilled, formless monotony. But even this ultimate entropy, this heat death, should not summon only melancholy. Instead, it invites reflection on the astonishing vibrancy of today's universe. Consider how remarkable it is that, for billions of years, gradients and differences persist. That energy flows from star to planet, from seed to flower, from birth to memory to dream. Life, complexity, art, and awareness all flourish in the era before equilibrium. Your very existence, and the warmth you feel tonight, are part of the ongoing dance that temporarily holds entropy's final quiet at bay. In the same way, despite knowing that bedtime spells the day's end, you cherish sunsets, laughter, and the comfort of rest. So too with the cosmos. Its entropic destiny only deepens the beauty of all the patterns, possibilities, and brief order that arise on the winding road towards equilibrium. Allow yourself, as you ease into the gentle hours, to marvel at this paradox. Entropy may one day bring perfect quiet, but it also permits the fireworks of creation, the emergence of galaxies, life, love, and all the fleeting order that makes the universe and your journey through it so exquisitely meaningful. Living with entropy is the essence of every human endeavor, a subtle dance of creating order, resisting decay, and learning to work within nature's quiet, unbreakable rules. It is the story of life, not just surviving but flourishing on a planet where gradients of temperature, concentration, and energy deliver both challenges and opportunities for beauty and invention. Every morning when you make your bed, sweep the floor, or tidy your workspace, you are gently pushing back against entropy, carving out small islands of order. The effort is never wasted, even though every act of cleaning or organizing is inevitably followed by a slow drift back toward randomness. The neatly made bed will become crumpled, dust will return, objects will scatter, and the process will need to be repeated. But in each act, order is created locally at the cost of dispersing energy. Your body's muscle contractions burning food, your movements creating little pulses of heat, your brain drawing glucose and oxygen to fuel thought and planning. Entropy increases overall, even as your space, momentarily, feels more serene. Architecture is a grander form of this same impulse. Cities are raised from chaos by design and labor, their streets, parks, and buildings maintained only through continual effort. Over time, bricks crumble, paint peels, and machines age, all evidence of entropy's subtle tide. Yet communities persist by channeling new energy, human creativity, sunlight, electricity, to restore and reinvent spaces. The very act of civilization is founded on slowing, redirecting, and creatively outpacing the inevitable rise in disorder, at least within the boundaries we care about. Suddenly, you may notice that all entertainment, too, is a wrestling with entropy. Whether keeping musical instruments tuned, libraries dusted, digital files error-free, or language precise, human culture is a living experiment in resisting the easy slide into randomness. Your own body, as you've seen, is perhaps the most intricate example of living with entropy. Each day, nutrition, sleep, and care are the nurturing forces that allow you to renew, repair, and recover, maintaining complex order against physical, chemical, and even informational decay. Medical science works hand in hand with the body's own wisdom, mending bones, eradicating disease, enhancing the internal balancing act that keeps entropy's effects at bay for as long as possible. And so, even our health and the stories of triumph over illness or injury can be understood as a poignant triumph over disorder, paid for, as ever, by hidden increases in entropy elsewhere in the environment. On a grand scale, humanity's ongoing quest to harness the world's resources is shaped by our understanding of entropy. We build engines and power plants knowing that some energy will always be lost as waste heat. Scientists design batteries, solar panels, and chemical processes, always aware that absolute efficiency, a world without waste, is forbidden by the second law. Sustainable technologies and circular economies seek to use resources wisely, slowing the rate at which useful energy is spent and disorder increases, but always accepting that some part must be dispersed. Information technology, too, is an arena of creative negotiation with entropy. Modern computers battle the randomizing effects of noise, wear, and time. Error correction, redundant systems, and regular maintenance are required to sustain the orderly flow of data. Even deleting a file or transmitting a message produces a subtle burst of entropy, a tiny echo of the irreversible choices that underlie any action. Yet there is artistry in the effort. Gardening, painting, composing, and raising children are all pursuits where lasting order and meaning are coaxed from fleeting moments. The lessons of entropy can lend grace to each project, reminding you that beauty is most precious because it is temporary, every accomplishment a gentle victory against the statistical odds. Living with entropy also means embracing the messier side of existence. Rather than becoming disheartened by the inevitability of change, you might find comfort in entropy's impartiality. The regular rhythm of resetting, restoring, and reimagining is the pulse of growth. It is why we revisit our goals, reinvent our routines, and repair what time has scattered. Even your nightly rest is part of this exchange. You dissipate heat, your muscles relax, your body enters a mode of repair, and in the morning you rise, ready to build order anew. Friends, families, and communities perform this dance together, supporting one another, sharing resources, and finding meaning in the act of creation and renewal. So living with entropy is not about defeat, but participation. It is about movement, adaptability, and the understanding that your choices, however small, matter in shaping experience, comfort, and meaning, even as the larger universe quietly, inexorably unfolds along entropy's arrow. Each breath you take, each story you live, contributes to a greater tapestry, one where order and disorder move hand in hand, shaping a reality as precious and dynamic as the fading warmth of a memory or the first rays of sunrise breaking the night. Embracing entropy means inviting a new way of seeing, one that recognizes not only the persistent rise of disorder, but the endless creativity, resilience, and possibility that this principle brings to every moment of existence. In the gentle dark, as your thoughts quiet and your breath steadies, consider how understanding entropy invites you to celebrate the rare, precious islands of order that emerge and to cultivate peace with the inevitable ebb and flow of life. Entropy teaches us the profound humility of being part of a much larger story, All things, stars, oceans, forests, civilizations, and even our own bodies, exist as temporary eddies in the cosmic current, shaped by the dance between order and chaos. The molecules in your hands once spun in the hearts of ancient stars, scattered and reassembled through countless cycles of creation and dispersal. Every act of organization, every relationship, every fleeting achievement or heartbreak exists within the context of this wider universe of possibility. Holding this truth can shift your sense of purpose and reduce the weight of perfection. It reminds you that change, loss, and innovation are not failures, but part of the unfolding order of things. In daily life, embracing entropy might mean finding a quieter joy in the creative process, knowing your efforts to bring structure, whether cooking, gardening, building, or caring, are meaningful not because they last forever, but because they stand as luminous moments of intention against a backdrop where effortless drift is the rule. When a home grows messy, a project ends, or even a cherished memory begins to fade, you can acknowledge this as a sharing in the world's most universal rhythm. Each ending, each scattering, is an invitation to begin again, to participate once more in the dance of emergence and renewal. This perspective also opens space for compassion, both to others and to yourself. Just as entropy challenges all forms and plans, so too is it merciful. There will be times when things unravel, when plans or routines dissolve. This is not proof of weakness or error, but a gentle echo of the way the universe itself unfolds. Knowing this, you can allow yourself to rest, to forgive impermanence, and to greet each new day with openness and curiosity. Unfazed by the certainty that perfection is always fleeting, at a deeper level, entropy reveals that diversity, fluctuation, and surprise are intrinsic to reality. Because disorder is so probable, each flash of order, every snowflake, every new idea, every growing leaf, is a true marvel. The temporary, improbable organization that makes life and consciousness possible is not a brief respite from a flawed cosmos, but a testament to the universe's astonishing generative richness. When you embrace entropy fully, you release the compulsion for absolute control and make room for wonder. You see that entropy is not merely a slow fade, but also the wellspring of invention and adaptation, a principle that ensures each day brings something unrepeatable, that no field, sky, or friendship ever returns in exactly the same form. This is the gift of entropy, a world always poised for discovery, and a gentle permission to rest in what is good, even as it changes before your eyes. As you prepare for sleep, let entropy's lessons wrap around you softly. Feel the peace of letting go, of understanding that even as things loosen and drift, you are part of a universe endlessly remixing itself, and that your moments of warmth, clarity, and connection are genuine wonders. To embrace entropy is to live with courage, gratitude, and grace, trusting that even in letting go and drifting toward night, you remain an essential part of the ever-evolving story written by this quiet, invisible force.